In this video, we discussed about the numerical overcurrent relay coordinations, which is another features we can do in this numerical overcurrent relay kit. Before we begin the experiment, let's understand the two types of relay involved. That is the primary and backup relays. The primary relay is the first to operate and isolate a fault in its designated sections. Its role is to ensure that any fault in its section is cleared as quickly as possible. On the other hand, the backup relay is designed to operate only if the primary relay fails. It is set to act after a certain delay, ensuring reliability and redundancy in the system. The objective of this experiment is to determine the appropriate relay settings for the upstream relay or the backup relay known as R1 and the downstream relay known as R2 or the primary relay in order to achieve the effective coordination between the relays on a model distribution line. The result will be verified by checking the time current characteristics of both relays during fault. In our experiment, we have a distribution line model. The relay R2 is placed between B and C, tasked with protecting the line section C to D. The relay R1 is positioned on the source side near point A to protect the section AB and more importantly to act as a backup protection relay for the section CD. In the event of a fault occurring between C and D, the expected behavior is R2 detect and clear the fault, which act as a primary relay. If R2 fails to operate, then R1 should act after a defined delay, ensuring that the fault is cleared. To connect the R2 breaker between B and C in the circuit, first take a wire from F3 point and connect it to the in terminal of the R2 breaker as shown in the numerical relay kit. Then take another wire from the next F3 point and connect it to the out terminal of the R2 breaker. With this breaker, the R2 breaker is now clearly connected between the points B and C and is responsible for protecting the section C to D. Any fault occurring in the CD section will now be detected by this R2 relay, which will trip the R2 breaker to isolate the fault. In this section, we will determine the appropriate relay settings for relay R2 and relay R1 based on the following coordination requirement. A fault at F3 must cause relay R2 to trip within 2 seconds. The fault at the same must also cause relay R1 to trip within 4 seconds. Act as a backup with a coordination time interval of 2 seconds. We will use the IEEE moderate inverse time current characteristics curve, and we need the following data for relay settings of these two relays R1 and R2. To determine the pickup current settings for relay R1 and R2, so at fault point F3, the fault current seen by the relay is IF3. This current is used to determine the time multiplier settings for relay R2 and R1 relay designated as TMS2 and TMS1. To determine the pickup current setting for relay R1 and R2, we follow standard protection coordination principles. For that, we need the fault current, the minimum fault current seen by both the relay, which is a fault occurring at the point Fy. That is the IFI current is needed to find the pickup current. Upon launching the software, 3 core modules are available to explore: fault current determination, numerical overcurrent relay experiment, and relay coordination experiment. Begin by clicking on the fault current determination module to find the fault current at location F3. A new interface appears. Click Establish a connection to relay, which is to communicate with the relay hardware. A message like relay not found. Please check the connection. If you see this message, it means the system is unable to detect the relay hardware. This usually happens due to one of the following reasons. First of all, USB cable is not connected, or the reset pin on the relay kit not pressed. Ensure the USB cable is properly connected. Then press the reset pin on the hardware to initiate communication. Now I verify the USB connection, but the establish connection button is still inactive. It becomes active only after completing the proper sequence. Then first click on measure fault current and press on continue. Then press the reset pin again and again press on continue. Now the established a connection to the relay button is active. Click it and the message connection successful will appear. In the hardware setup, please connect the patch code from the fault switch to fault point F3 to create the fault condition at that location. Next, click the measured fault current button. After this, a message will be displayed showing the fault current during the fault at point F3. It shows around 6.82 ampere. Please click here to close to exit the message and then press the reset button to perform another test. Please repeat the experiment at any other desired fault point to measure the corresponding fault current. After the fault current determinations, the fault current at F3 and the location F5 are tabulated in this table. F3 is found to be 6.82 ampere and F5 is 4.08 ampere. So, to ensure the proper relay coordination and avoid undesirable tripping under normal operating condition, the pickup current of each relay must be selected between the maximum load current and the 80% of the minimum fault current. In this case, the minimum fault current seen by both the relay at the fault location F5. The selection can be mathematically expressed as follows. In our experimental setup, the load consists of LED indicators which draw relatively very low current. Hence, we assume that both the relay R1 and R2 carry the same load current of around 2 ampere. And the other upper limit is around 80% of this 4.02 come around 3.2 ampere. Therefore, we select the pickup current of both the relays, that is the backup relay R1 and the primary relay R2 as 3 ampere. So with this, it is able to determine the time multiplier settings of relay R1. In this case study, here to maintain a CT of 2 seconds between the relays, the R1 should trip within 4 seconds for a fault at F3. Therefore, the value of TMS1 for relay R1 is calculated as follows. This is the IEEE moderate curve equations. With this, the only unknown is TMS1. Using this equation, the TMS1 is calculated as 1.22. Similarly, to calculate the time multiplier setting TMS2 of the relay R2 in order to achieve the tripping within 2 seconds for the fault at the same location F3. The calculation procedure is given below. 2 seconds is equal to IEEE moderate equation into TMS2. Here also the only unknown is TMS2. Finally, the appropriate value of TMS2 is calculated as 0.61 to achieve a tripping time of around 2 seconds. Finally, the final relay settings are tabulated here. The two relay R1 and relay R2 both use IEEE moderate inverse curve. The pickup current of both the relay is 3 ampere and the TMS of R1 is 1.22 and R2 is around 0.61. The expected graph is shown in this right side. Here it is clearly visible that the fault at F3, the current is IF3, and this IF3 current, the relay R2 will trip within 2 seconds and R1 will trip within 4 seconds if the relay R1 fails. That's to maintain a CT of around 2 seconds. Welcome to the demonstration of the relay coordination experiment. using our numerical relay training kit. To begin, click on the Relay Coordination Experiment button on the main interface. Once the experiment window opens, select Establish Connection to Relay. This action initiates communication with the relay. If the communication is successful, you will receive a confirmation message and the interface will become active for further configuration. Now proceed to select the coordination point. In this case study, the R2 breaker is connected between the F3 points. So from this drop-down menu, we can select that the R2 breaker is placed between the F3 point. Suddenly you can view that the R2 breaker in this status window is placed between the F3 point. Next, enter the relay settings for both the upstream or backup relay R1 and the downstream or primary relay R2 based on this coordination scenario. So in this case study, we already calculated the pickup current of relay R1 is 3 ampere, R2 is also 3 ampere. Both the relay curve is IEEE moderate inverse curve. The TMS of R1 is 1.22. The TMS of R2 relay is 0.61. You can view the interactive relay chart. So it's the time to verify the performance of our coordination settings before proceeding to the actual experiment. So we know that at F3 point, the fault current is around 6.82 ampere. For this current in this graph, zoom on that part of the relay curve and check that with the help of this cursor at 6.8, around 6.79 ampere, the R2 will trip around 2 seconds. Here it is 1.96 and R1 relay will trip around 4 seconds. Here it is 3.93 seconds. This results in a coordination time interval of around 2 seconds, which ensure proper selectivity. That is, R2 will isolate the fault first, while R1 remain as a backup protection in case of R2 fail. This visual confirmation helps reinforce the principle of time-graded protection and validates the relay coordination logic applied in this case study. Once the relay settings are entered and the coordination is verified, proceed to click on Update Settings to Relay. This step sends the configured protection parameter to both the relay in the kits. After successful update, close both the breaker in the relay kit to complete the circuit. This update a healthy operational condition, allowing the relays to monitor the line and respond to any fault as per the newly applied setting. Next, click on the plot waveform button. This will display the current waveform along with the trip indication of and R2. To simulate a fault condition, click on the fault insertion button. Now create a fault at the F3 point by ensuring that the patch cord from the fault switch is properly connected to the F3 terminals on the relay kit. Once the relay is initiated, fault is initiated at this point, observe the system response. Here the relay R2 will trip after 1.93 seconds, that is near to the 2 seconds as per the earlier settings, which is responsible for protecting this section CD. This confirms that the relay coordination is functional correctly, with the downstream relay operating first to isolate the fault. So please click here to close. To get a clear view of the waveform details, click on the zoom on button here. This feature provided an enlarged view of the aligned waveform, making it easier to analyze the current and relay trip signals with respect to the time axis. Click on the generator button. Report button facilitate detailed documentation of this event. Shows relay settings of both the relays, result, curve, relay curve, detailed waveform. So this hardware kit also offers an important feature to simulate primary relay failure, allowing user to observe how the backup protection operates. For that, please click on the reset relay, which will clear all the data and again established a connection to the relay. Here you can observe that here a checkbox will appear here. So to fail this R2 relay, simply click the checkbox labeled "Tick here to fail R2 breaker." This setting simulates a scenario where relay R2 fails to operate under fault condition. After enabling this option, update the settings to the relay, because already settings are available. The previous settings are available here. And just click on update settings to the relay. This will again close both the breaker R1 and R2, and all the LEDs in the relay kits are turned on now. In this case, since R2 is intentionally failed, create a fault at the F3 point, just as done in the earlier case. In this case, since R2 is intentionally failed, it will not trip even though it detects the fault. As a result, relay R1, which serves as a backup relay, will trip within 4 seconds. That you can see from in an enlarged view here. This come around 4 seconds, clearing the fault and ensuring the system protection. So here in this status view also you can see that R2 is failed to trip. It is still on, but R1 is tripped within 4 seconds and act as a backup protection for this line. This feature helps trainees understand the importance of backup relay coordination in case of primary protection failure, a critical aspect of power system reliabilities. Reset the relay and proceed with another case study.